Hello, quick video on sample statistics and how we can use them. Well, usually we're working from a sample, aren't we? We don't know the whole population of data. We may know about 10 people, 20 people, something like that. And therefore, what's really useful is to use the sample mean and occasionally standard deviation to find our population mean, and occasionally it's standard deviation as well. And there are two formulae here, mathematical formulae, that we're going to work out. Particularly the second one has some very useful properties that allows us to accurately find out what our population mean is from a sample. Okay, let's use an example here, shall we? Okay, we measure the heights of 150 sixth formers, they're all males, so we've got a homogeneous group. Here's the data, let's have a quick look here, there it is. So here you can see in the spreadsheet all the different heights, and they range from about 160 up to nearly 200, don't they? There's a couple in the 90s here. There we go. So there's our population. And if we look at the population, we can find its mean, it's 173.5, and its standard deviation is 6.49 centimeters. Okay, so on the right hand side here, we've got a nice little, it's pretty normally distributed, so I've drawn a little normal diagram with those parameters. Okay, let's take a sample of 5 heights. The first 5 in the list, 170.1, 172.2, etc., through to 168.9. Well, if we find the sample of the mean of this little sample, we find it's 173.38. That's pretty close, isn't it, to the population mean? And if you think about it, that's pretty logical, isn't it? I've marked our points here in green little crosses, and if we find the average of the 5 points, we're going to find something in the middle, and isn't it? The extreme values get shaved off. And in fact, what we're really looking at something is, because of that, we result in each of these samples is actually sort of statistically going to be narrowed down from an individual point, isn't it? If we take a sample of 5, the mean of that sample is going to be narrower, so we're going to have a narrower PDF. But what's the maths of that? And we'll work our way through using this data. Okay, so if I now took 20 samples of 5, so our first one had a mean of 173.38 we saw above, take our next 5, it's 174.36, and we go through and we've got 20 of those, so the last one's 169.46. So what I'm now going to do is look at the mean of these means. Yeah, each one above is a mean. So we're doing the mean of means, and it's worth trying to get that in your head as a sort of words to use, mean of means. So here, of these means, the mean of these means is 173.9, which is again quite close to population mean. But we can also calculate the standard deviation of these means, and we get 3.5 centimeters here, which is smaller than the 6.5 for the population. Would we expect that? Yeah, because it's going to be there's going to be less variation in these means. Yeah. But we can follow on this approach. What we could do is take a slightly bigger sample. Let's have a go here. Excuse me, here. So let's say each sample has now got 10 students in it. And again, we take 20 samples. So the mean of the first 10 students is 176.4, and of the next 10 it's 173.0, all the way to the 170.6 here. Okay, so we can get statistics on these means, and we get 173.3 is the mean of the means. And now our standard deviation of the means is narrowed even further to 2.3 centimeters, which is what we'd expect. The bigger the sample, the more likely the mean is going to be near the middle, so the standard deviation is going to be less. Yeah, it's getting smaller and smaller. Okay, let's carry on with that approach. Excuse me, let's just get up to here so I can get it on the screen. There we go. So we've done that for samples of 5 and 10 individuals. If we're now going up to 15, 20, 30 and 50 students in each sample. And what I've done here is graph the results. So if we look at the mean first, and the sample size is on the bottom and the heights is on the vertical, then what we're seeing here is a very sort of straight line here, isn't it? Pretty well all the means in the here are 173. Doesn't matter, it doesn't vary with sample size at all. But let's have a look at standard deviation here. So our original population, if we just took one item out of it, one individual out of the 150, that's our 6.5. Then we had, from our 5, we had 3.5, didn't we? And then we had 2.3. And I've extended it down here, so the last one here is for the 50, a sample of 50 items, and the standard deviation of the mean of those means is more like 1.5 or something, isn't it? I asked the spreadsheet to do a power correlation, and I've got this formula here, and it's got very high correlation, 95% correlation here, and we've got two parts to this, haven't we? The first bit is a constant. Well, that 6.57 looks awfully like the 6.5, which was our population standard deviation, wasn't it? And then we've got this power here. It says x to the minus 0.464. Of course, x here is the sample size, so we'd think of it as n normally. So what we've got here is something that's awfully close to x to the power minus a half, isn't it? And actually, mathematically, we can prove that to be true. So the sample standard deviation is going to be our population standard deviation over the square root of n, where n is the sample size. Yeah, we okay with that idea? That's got some, so that's quite useful, isn't it? And as I say, we can prove using some algebra that that's true, that the sample standard deviation is the population standard deviation divided by root n. This is going to prove to be very useful for us because this property of narrowing means we can get some pretty accurate results from it. So, and there's two ways we can use this, either in hypothesis testing, which we're going to use in S2, or confidence intervals, which I think is in S3 in MEI. Okay, let's start by having a hypothesis testing there. All right, so for hypothesis testing, we need a test statistic. Our test statistic in this case is how far our sample mean is away from our population mean, but we've got to measure it in standard deviations, and we're doing it in standard deviations of the means, not of the main population. So on the top here, we can create this as our Z, assuming this is a normal distribution, which this one looks like. Here we've got our sample mean, take away our population mean on the top. Oh, there we go. And then we've got to divide it by our standard deviations of the sample, which is population standard deviation divided by root n. If we plug those numbers in here, our sample mean was 173.38, our population mean was 173.5. We know the population standard deviation is 6.49, and usually we know that from long run data, and our sample is 0.5. So we get a Z value of minus 0.04. If we then look up in our tables the value of that, we're going to get from our table 0.516, and as it's negative we have to go 1 minus. So here we've got a probability for 0.48, which is 48%, yeah? So it's very likely here, isn't it? We're right near the middle. It's very likely that this came from our base population. And so what we're saying is not significant, H0 accepted, and it comes from our population. Now, the other way of using it is confidence intervals, which is an extremely useful property. What's a confidence interval? Well, if we know what our sample mean is, what we're interested in doing, there we go, sample mean of 173.38, what we want to do is try and find out where the population mean is. And so we start with this value, that's where our sample mean is, and we can then work out how far it's likely to be away from that. Now, we can't often do this with 95% confidence, so what we're interested in is how many standard deviations is it likely to be away from this value. Well, first thing that's important is we're looking at sample means. So the sample mean standard deviation is our population of 6.5 divided by square root 5. So that's narrowed our standard deviation, hasn't it, to 2.9 for our sample, yeah, sample means. So that's really useful because it's it's improving the accuracy of our sampling, sorry, of our estimate. Okay, and the other thing we just need to bear in mind is if we're looking at a 95% level, well, we can use our normal probabilities, and we know that 95% would give us 1.96 standard deviations, wouldn't it, within. So we're going to use that as well. So if we want to know our range, well, we know that it's our sample mean, which is our 173.38, and then we've got our plus or minus section. So it's plus or minus 1.96 standard deviations. And 1.96 and standard deviations we know is 6.5 divided by root 5. That's our 2.9. So 2.9 times 1.96 is 5.7. So we've got 173.38 plus or minus 5.7. And so we've got a range here that we think that the population mean is between 167.7 to 179.1 centimetres in 95% of the cases. So that's quite a narrow window, isn't it, for us to be working in. And that's what makes this property very useful. Okay, so finally, let's have our little summary at the end. So if we take a sample from a population, we can find the statistics of the sample sample means, and we can find the mean of means, and the standard deviation of means. Okay, and the mean of means is going to put the population mean, and the standard deviation of means is going to be the population standard deviation divided by root n. So as we see here in the green, we're going to get a narrowed normal distribution from our population by dividing by root n. This narrowing is extremely useful for confidence intervals or for hypothesis testing. And remember that the larger the sample, the more accurate the result's going to be. There we go. Hope that's of use.